Okay, thank you very much for the introduction. My name is Christoph Brunner, and I will take over the first part, and after this, Bettina will make the second part. The topic is membrane distillation using waste heat and solar thermal energy as a very promising separation technology. But before I'm going into the technology, I just want to say 3 slides about our institute. AEE INTEC is a institute which is a non-universal research institute. We are founded in 1988 and we are situated in Austria, near Graz. This is in the south part of Austria. And we are working in this field of renewable energy and resource efficiency, very general speaking. We have 4 different areas where we are working in. On the one hand, research. Then we see our work very main based on applied research, so also development, technology which are not in the market yet, but which needs further push and further development. This is our focus. We are doing consultancy, but consultancy mainly for policy, for government organizations around the world, here in Austria, but also in Africa, in South America, in Asia. And then we have also a lot of training activities, also again around the world, where we are working together with different institutions like UNIDO or the Austrian Development Agency. Our institute is structured in 4 different departments. One department is dealing with building and retrofitting existing buildings, so optimizing these buildings. Another department is dealing with thermal energy technology and hybrid systems for buildings mainly, and also this combination of different renewable and energy networks. We have a big part also as a laboratory where we can do tests with different technologies where we're working on. And this department I'm head on is the department on industrial processes and energy systems. We have 4 different areas where we're working in. One area is on system optimization of industry in general. So we look how to optimize the energy use in a company, in a producing company, where we use the methodology of a pinch analysis, mainly to optimize the heat exchangers which are set there, to optimize the storages which are used. Then we are looking also the role of the industry in an energy system, how to how industry is interacting with district heating networks and electrical grid networks. We have one specific focus on solar process heat, so how to apply solar thermal energy for the industry. I was coordinating several networks on the IEA, SHC, TCP group, and also leading different European projects in this field. And then we have this part where we today want to focus on. We also have a look on specific technologies, process technologies, and one of these specific process technology is this membrane distillation. Yeah, this was the general overview about AEE INTEC, and now coming to the technology itself. So what is membrane distillation? It's a thermal separation process. So compared to other membrane technologies, which are running on electricity, membrane distillation is really running on thermal energy. And we have, on the one hand, a feed stream, which is hot, and on the other hand, a permeate stream, which is cold, colder than the feed stream, let's say. And then in the middle, we have a hydrophilic porous membrane. Due to the fact that there's a pressure difference between the feed stream and the permeate stream, vapor is going through the membrane. So only vapor is going through and condensates on the other side. So this is the general concept behind it. We have here, I hope this is working with the pointer. No? Okay, you see a similar, like a Gore-Tex jacket, what maybe all of you knows, this membrane distillation works. So with the Gore-Tex jacket also, in that form, the train should not go through this jacket, and when you're sweating, vapor should evaporate through this jacket. So important is that there's a difference of temperature between the hot feed stream and the cold bare stream. The temperature should be in this range of about 25 to 30 degrees, and everything is running at atmospheric pressure. So the big advantage of the membrane distillation is on the one side that you have as a product, if you separate water, for example, a pure distillate on the permeate side. The whole operation works at atmospheric pressure, even if you don't need temperatures higher than, for example, 80 degrees. So the evaporation works between 30 and 80 degrees. So the feed stream just has to be heated up between 30 and 80 degrees. What does it mean this in regards on energy? You can use an energy source, for example, waste heat from the industry, which are at this low temperature and which you don't need anymore in your industry, for example. Or you can perfectly use solar thermal energy, which is more efficient at this lower temperature. You have in the whole system a reduced electrical costs compared to other membrane technologies like ultrafiltration, because you just have to need the electrical energy for pumping, but you don't have to press the feed stream through the membrane, for example. You can operate at very high concentration, so the feed stream can be concentrated very high up to a crystallization point. So this is very unique compared to other membrane technologies. You have less fouling, and this means that also the costs for cleaning are much lower than compared to other technologies. Why do you have less fouling? Because you don't have to press the feed stream through the membrane. It's just a vapor which goes through the membrane, and that's the reason that the fouling is reduced. And the application in low temperature, at low temperature, has a very positive effect also for liquids which are very sensitive. If you have some products in it which are sensitive to high temperatures, then this technology fits very well. There are different possibilities how membrane distillation can configure it. The most known configuration is the, here's the error, if you can see it. The most known is the direct contact membrane distillation. What does it mean? So similar what I showed you before, we have a hot feed stream and a cold permeate stream. In the middle we have the membrane, and so it is directly contacted, the permeate, to the membrane itself. And then we have different other ones. We have the air gap membrane distillation, so there's not a direct contact to the membrane, but there's an air channel in between. We have the possibility to have a sweeping gas, which takes the permeate and condensates outside the module. And we have the possibility to use vacuum, and for certain applications this makes big sense to use this vacuum on the permeate side. I will show you later on mainly this direct contact membrane distillation configuration and an example on the vacuum membrane distillation, but to separate volatiles out of different waste streams. Yeah, coming to a certain overview, where you can use, or where the different applications of the membrane distillation could be. So again, what you can see here is the membrane itself. Steam goes through the membrane. We have again the hot feed stream and the cold permeate stream. And in these examples, we want to separate water from these feed streams. And now we have two possibilities. We have the one possibility to use the water as a product. So we have a certain feed stream for with some concentration, or a wastewater stream, for example, and we want to separate out of this wastewater stream water, and this can be done by this configuration of the membrane distillation. So examples would be desalination. This is let's say more or less the original application of the membrane distillation. Or, for example, in a galvanic industry, the recovery of the rinsing water of a galvanic bath. The other possibility to separate water is to concentrate the product for further reuse. So now, not the permeate as a pure water is my product, but it is also it is more important to have here a high concentrated stream which can be further reused. So we have, for example, a chemical bath with some metals in it, and we want to recover these metals, and if we get rid of the water here inside to concentrate the stream, then I can reuse these metals. Examples is, as I said here, metal recovery from rinsing water, or, for example, the juice production, or to concentrate the CO2 in a wastewater treatment plant, or, for example, what we also have one example in the pulp and paper industry, to higher the concentration of the black liquor, and in following to burn this black liquor. So these are the possibilities when we want to separate water within a membrane distillation. Another possibility, there's one example on this. This is an example from the printed circuit board industry. We have a bath, a gold bath, active gold bath, and we have here rinsing water which is diluting this gold bath, and by separating with the membrane distillation the water out of this diluted gold bath, we can recover, we higher the concentration again, and we can recover this gold bath. And by this example, in this printed circuit board industry, this company is saving a lot of gold, and then of course also a lot of money by recovering the gold in this specific gold bath. Yeah, coming to the other application, here now we not water is going through the membrane. It's not going through the membrane, but volatiles. So we have a certain feed stream again, with including some volatiles, and we want to recover these volatiles. Here again, we have two possibilities. On the one hand, we want to use these volatiles as a product. So volatiles are separating from the feed stream, going through the membrane, and are collected at the permeate site. Examples are here the recovery of ammonia. On the one hand, to use it as a fertilizer, for example, or further energy used in the fuel cells, or recovery of aroma components in a feed stream, or, for example, to separate alcohols out of beer or wine to produce alcohol-free beer, for example. And again, we have the possibility also to use this stream, the feed stream, which is higher, where there's a higher concentration. and not use the volatiles again. Here, for example, we applied the membrane distillation in the wastewater treatment plant in order to separate ammonia out of the wastewater, and so to lower the energy demand of this wastewater treatment plant, or to separate ammonia, for example, from the residues of a biogas plant in order to bring these residues on the field without any restrictions regarding the ammonium content. Okay, here we have one example again regarding the separation of ammonia with wastewater with an MT for ammonium separation. So we have a wastewater stream containing ammonia. The MT is separating ammonia with the MT, with the membrane distillation, and this ammonia can be used either in gas. So we would need here this technology of vacuum to produce gas, and this gas is directly feeding in the fuel cell, or we are producing a liquid, a condensate, this ammonium sulfate, for example, and this ammonium sulfate is a basic product for fertilizers, and it can be used then for different other applications. Fine. So coming to the next slide. So these are potential different industries where we see a big potential to use the MT technology. Of course, it's in the mining industry. What we see, it's a galvanic industry. This example is what I showed you before, and Bettina will speak a little bit later in more detail about it. Desalination, I mentioned, chemical industry. We see a big potential. Pulp and paper industry, as I mentioned, with the black liquor concentration. Then in the food and beverage industry, we have here examples in the sugar industry, but also in the in dairies. Bio-based industry in general, everywhere where we want to higher the concentration, for example, here we have a big potential, but also wastewater treatment plant, this example what I presented before, where we separated the ammonia and so lower the energy demand for wastewater treatment plants. These are from AEE INTEC, let's say our different steps what we can offer. So we can do experimental studies in our lab. So really first studies and also with our lab plants inside our lab, we can do with small amounts of feed streams different experiments. We also are developing models. We have here a computer program where we can simulate different configurations of the model and then build up prototypes of these different models. We have also a pilot plant design, which is in a container. I show later on a picture on it. And what is also one strength of my department, that we can work in the system integration. We need to think about how to integrate this technology based energy-wise. So means using renewable energy, for example, like solar process heat, but also using the waste heat in the best form under considerations of temperatures, at which temperatures this waste heat are available. Then, here these the picture of our on the one hand, our pilot plant, which is in a container, so it's a mobile container, which at the moment is, for example, operating at the galvanic industry. And we have here our lab plant. As you can see here, we are working here with smaller devices, smaller models, where we really can test the membrane itself. On the market, you can find not that much, but a few companies which offer the motors itself in different sizes. So we have, for example, a company, Solar Springs from Germany. They are offering these smaller lab facilities and test facilities, also in pilot plant scale. We have EFCON, which is quite a new company, also situated in Germany, which is doing larger applications, and Aquasteel, this is also one company where we already worked with. At the end, I just want to highlight a few benchmarks, also compared to ultrafiltration. So, of course, it's always a little bit difficult to tell you absolute values or the absolute numbers, but this is out of our different tests and applications. We could see that the energy demand of the membrane distillation, the thermal energy demand lies between 280 and 700 kilowatt hours per cubic meter per minute, what is produced. This depends, this range depends on the one hand on the operating temperature. When we are operating at lower temperature, more energy is required. Also, it depends on the internal heat recovery or on the different properties of the liquid which is used as a feed stream. If you can use, for example, waste heat, this number can be reduced. Let's say you can more or less cover this 280 or this 700 kilowatt hours by 100% of the waste heat out of a company, for example. And then the costs of the energy which has to be produced can be quite low or is near zero. And here you have in comparison between ultrafiltration, UF, and the membrane distillation, a comparison regards of the costs, the operational costs. So we have on the first line the membrane change, so the cost of the membrane if you have to change the membrane after a while. So for ultrafiltration it's about 0.05 euros, and for the MD it's 0.02 euros. The energy costs, it's much lower at the MD part compared to the ultrafiltration. The cleaning costs are a little bit higher at the UF, and but the total cost compared, you can see here, I forget this is one example, but you can see here we are lower than the costs at the ultrafiltration. Okay, so I'm at the end of my presentation, and I will hand over now to Bettina, and she will go now in a little bit more in detail of different applications.
Good afternoon, everybody. My name is Bettina. I work in Christoph's research group, and yeah, we've been working with membrane distillation on various applications, as Christoph has shown you, and I would like to highlight two applications which I think are hopefully most closely linked also to your backgrounds. However, in the beginning, I would like to repeat a little bit the work we do at AEE INTEC when we work with industrial projects on membrane distillation. So as Christoph has shown you in an overview slide, this is now a little bit more in detail. When we have a certain industrial company approaching us with a water problem, what we usually start with is specifying which kind of membrane material can be used or could be applicable for this process. And we can do so by doing hydrophobicity tests, so checking that the membrane which must be hydrophobic in membrane distillation, is it really a hydrophobic also, and does it remain its hydrophobicity throughout the tests? How is chemical resistance, is that a topic? Usually this is not a topic. However, if we really work with the galvanic industry and we have pH values of liquids down to 2 or even less, this is just something that's important to look at. However, so far we've never had any problems in that respect. And also we have the ability to do physical stability tests by testing the liquid entry pressures of the membrane. Then, as Christoph showed you, we have the expertise to do modules. So depending on the, let's say, the project or the requirement from the industry, we can run numerical simulations as a basis for specific module configurations. We can also do so in the beginning to check which module configurations could be best suitable for the specific problem that we are really facing. What does it mean? Module configuration, basically we define the geometrical parameters of the module, the configuration, how it's put together. There is some various details that we can choose from in the detailed module design. That also depends, of course, on temperature profiles, etc. So, as I just said, closely linked to temperature profiles, as these temperatures really are the driving force for the transmembrane flux, because it is the main driving force is really the difference in partial pressure, in vapor pressure, the vapor pressure difference, and this is closely linked to the temperatures. We can then also go a step further in designing a whole membrane distillation plant, which means now that we might use several modules to fulfill a certain task. So one module has a certain amount of membrane area and a certain configuration, and we can now put these modules either in series or in parallel. And this is also the, let's say, the analysis or evaluation of the best suited plant design is usually done by simulation programs to optimize that. Christoph already mentioned our container module assembly. In certain cases, when we have really own module configurations, we can also assemble those at our labs. And about the experiments, again, usually it's really important for us to follow first preliminary feasibility tests, and then together with lab scale experiments, and then later go into the demonstration plants. Why is this so important? There's a lot of work on preliminary tests being done. There is also quite some information available on with lab plan studies. However, to really evaluate the industrial performance, also under industrial configurations, we just need really the tests with our containers on site, because only then we can really see what is going on over a longer time. We see the changes and fluctuations of the industrial process and can tune the MD installation best to fit to those requirements. Yeah, and an important point of the work is then also MD upscaling. So based on the lab or demo scale that we have to really come to a real system design. And to integrate, of course, the MD into the processes, and this is very closely linked then also with the question, where does the thermal energy come from? Do we have waste heat available on site, or do we have solar process heat? Do we have the ability to fuel, let's say, the process with solar process heat? And here, our combined expertise of energy efficiency, renewable energy in industry, and membrane distillation is an important factor. Yeah, the two examples I would like to, show you now in more detail is one from the galvanic industry and one from the electroplating industry. Starting off with the galvanic industry, here we have a project using membrane distillation for treating liquids which are liquids from the galvanic bath. And I think I best show you the setup in a small scheme, where you see now, looking where the pointer is, you see that in the galvanic industry we have several baths after each other, and in this specific industry we work with, we have, after a certain bath configuration, one passivation bath and then a followed rinsing bath before the metal parts, which are usually dipped into these baths and being transported further, and then after the rinsing also being transported further along the production line. In the passivation bath now, we enter with a passivation liquid. However, through the transport of the metals carry some of the passivation to the rinsing bath, and so the rinsing bath after a certain time accumulates with passivation liquid. What's usually done is that water is added to keep this concentration low, and that some wastewater is discarded. Now, the process optimization with MD, the concept is as follows, that this wastewater is basically treated with a membrane distillation unit. The concentrate of this, so the concentrated passivation liquid, the reconcentrated, is fed back to the passivation bath, whereas the ultra-pure, clean water is recirculated as rinsing water. Feasibility tests have shown that we can reach savings of water up to 93% and savings of passivation concentrate of about 60%. Based on these very positive figures, we have now started long-term tests in pipers with our container unit. The operating parameters in this unit are as such. We have 5 modules operating, and each of these modules is working with a 140 liter per hour flow rate of feed and permeate that are circulated over the modules. The temperature of the feed is 80 degrees, so we have 80 degrees of the fluid entering as a feed is heated up to 80 degrees, whereas on the cold side we have a permeate temperature of about 18 to 20 degrees. I will show you now how this looks in more detail. So usually in membrane distillation we have one feed cycle and one permeate cycle. The target temperatures, as I said now, was that we enter the module with a feed temperature of 80 degrees and on the other hand a permeate temperature of 18 to 20 degrees in this case. Which feed temperature is chosen is usually an output of the feasibility tests run in the lab scale. It can be that certain liquids have best parameters at higher temperatures. However, it can also be that certain liquids are better treated with lower temperatures. Influential factors is basically the chemistry of the feed stream. So, for example, we can have very temperature-sensitive feed streams that cannot be heated to higher temperatures because of its chemistry. We'll see an example later on with the electroplating industry. And on the other hand, we can also have as an influential factor in chemistry, for example, when we have a lot of organics in the feed stream, and that these organics at certain temperatures have different fouling properties. So also in that way we can tune or optimize the fouling phenomena with the temperature. Of course, the temperature is also an important factor of assessing our driving force, but this is mainly really because it's a difference in, it's the difference in the partial vapor pressure, so it's a vapor pressure difference that's mainly influencing the driving force, so it's really the difference between the temperature of the feed and the permeate, and not only the absolute temperature of the feed that is decisive here. So in this case, in the electroplating industry, in our container, we have now, as we said, the feed cycling over each module and the permeate cycling over each module. And obviously, the feed is reduced in temperature after it has flown over the module, and the temperature of the permeate has increased. So what's happening now is that we have a certain amount of heat recovery installed between the feed cycle and the permeate cycle. And this basically brings energy from the permeate, from the heated up permeate, back to the feed cycle and reduces the external heating demand. And at the same time, we also reduce the external cooling demand for the permeate cycle. And this heat recovery is actually very important. So the general combination here of heating and cooling is very important to really optimize the thermal performance and to reach these target figures that Christoph has shown you for the thermal energy demand in membrane distillation, which can be without heat recovery much, much higher. So yeah, as you can see here, our modules, we have in the container just basic tanks as a feed and permeate working tanks. Here you see our pure distillate tank, so really the product as a water. How is the long-term performance? This is of course very important, and this is usually one of the crucial questions in any membrane process. Is the membrane really stable? How is flux stable? Can we reach this? And as Christoph said, this is so closely linked to cleaning and to basically to the operating costs, and at the end of the day, of course, to the economics of the system. What we can see here that now when we run in pipers, we really have the possibility to run over very long time. So as you can see here, this graph goes over 10,000 minutes. So it's quite a long time. We actually have run even longer, so we've been running for several weeks already. What we can see here is that this is a very fresh project actually. So this data has been gathered just early autumn this year in 2018. And what we can see here is that we do have a certain flux degradation over this time, specifically in the beginning, but we also have to mention that at the same time we increase the concentration. So this is still the start of the measurements where we increase the concentration. You can also see it visibly over the optical verification how the passivation liquid has been increasing in its concentration. When we, on the other hand, now say we plot the flux degradation over a concentration factor in order to show this a little bit more in detail, we can see that we have a certain degradation of transmembrane flux when we go from, let's say, a basic concentration to a higher concentration. However, once we have reached a certain concentration, the influence of going to even higher concentration and flux shows a different picture. So we don't have a linear degradation as we go to very high concentrations, and this is where we can now really also show what Christoph has shown and explained in the beginning, that MD has the potential to really work at very high concentrations. Important for the industry, of course, is the quality of the material. So in this case, a comparison of passivating one plate with the original passivation bath and the concentrate from the MD. And this test was outstanding and performed very well. Energetical system integration is an important topic, as we mentioned. So in this case, we have been looking at waste heat available from the chillers, from air compressors, and from another process bath. And as we need a temperature of 80 degrees, and evaluating, let's say, how the waste heat potentials are, there is also a very strong possibility here to integrate solar process heat as potential energy source or in a combined way with waste heat. Another example Christoph has already shown you now comes from the electroplating industry. I'm not going into the details again of the process, as Christoph has explained already. The idea of integrating membrane distillation for the gold bath recovery. I would just like to highlight again that the importance of MD or its suitability is of course highlighted by the fact that if it's possible to reuse not only the concentrate that's gained, but also the clear water. So if we have a double effect here, this is of course has the highest potential. Also in this project, membrane stability has been checked in the beginning. Then membrane performance has been analyzed, and finally an own MD module was designed and the whole process, because also here a larger demonstration plant is just being installed within the next weeks. When we look at the laboratory tests of the gold solution being treated in an MD, we can see that we have very stable flux properties that we've found so far in lab scale. And in this case, of course, flux is much lower, but also I have to highlight here the temperature configurations. Here we have a temperature-sensitive liquid, and so we are able to really just heat the feed temperature to 35 degrees, work with a permeate temperature of 16 degrees, and still have a suitable process performance. Also here, the analytical results prove that the gold solution is reusable in plating for the electroplating tasks, and also that permeate is suitable in rinsing. So these quality tests have been performed. In the last month, just for this project, and the MD module has been designed in more detail based on the required absolute separation rate of 15 to 17 liters per hour, and we need a membrane area of 20 to 30 square meters for that. In this case, based on the temperatures available, on the one hand, we can integrate the waste heat of the chillers as thermal energy demand, and we can basically heat fresh cold water by cooling down the permeate. So the permeate is being cooled by fresh water, and this fresh water is preheated and is again used as warm water on site. What is important in this case is because we have very low temperatures here, heat recovery is not very well possible, which gives us a much higher thermal energy demand in this application. However, because the demand is just at that low temperatures, where usually waste heat is abundant in industry, this can easily be covered by the available waste heat. So in this case, it's not so much a matter of reducing the thermal energy demand for the concentration, but rather to make the available waste heat on site to give that a sensible usage and use it for the membrane distillation process. Yeah, the conclusions here, as we said, we could prove, or also for the electroplating industry, the stability of the membrane, the reusability of concentrate and permeate, and process design has just been made, and the demonstrator is still going to be installed this year. Some conclusions, some general conclusions for the copper industry from our regards. As we've seen today, MD delivers water at very high purity. It can remove volatiles, and if tuned correctly with the temperature settings, this can also lead to somehow a selective volatile removal, not selective based on a volatile structure, but based on temperatures and the volatility of substances. And we are able to treat liquids at very high concentrations, which leads us to the fact that we can have a very high concentration of process fluid as a product without having a large thermal or hydraulic stress of the medium itself. So MD has definitely the potential for wastewater treatment on the one hand, but also process fluid recovery. Thermal energy supply can be done with excess heat available, so low temperature waste heat can be used if that's suitable with the chemistry of the liquids. And solar thermal has here, of course, a very large potential as well. Challenges that that are there are fouling phenomena. So in these cases we've shown you now where we worked a lot with inorganic strains. This was not a big issue and good cleaning procedures could be found. This can be different when we work with very high organic concentrations, for example, where maybe more effort has to be put in the cleaning strategy. And it is very important to really look at the long-term operation and to identify the long-term stability of the whole MD process. With this, we would like to conclude from our side, and we are looking forward to have some discussion or questions. Thank you very much for your attention so far.